Hi, this is Ibrahim. Most of you already know me if you came from my 118B or 118A, and others I will get to know to the extent that's possible in this format. So let's start by reminding ourselves how derivatives are defined in Abbott or in Rudin when he's working in one dimension. So let's suppose we have a function f of a real variable, so it's defined on some open interval, maybe, taking on real values. And let's say x is some point in the domain. Then what's the derivative of f at this point x? So first of all, what type of thing is it? It's a number. If it exists, it's a number. So let's call it capital A. A real number is the derivative of f at x if and only if the limit that I'm going to write down exists and equals a. All right, and our goal is to upgrade this definition in two ways. First of all, we want to upgrade this output to higher dimensional output, so make this into Rn. And also, instead of looking at an open interval inside R, we'd like to upgrade that to be possibly higher dimensional. We'd like this to be, we'd like the domain to possibly be any subset of Rn. Okay, so let's talk about what needs to change. So before we make any changes, let's rewrite this statement. Here's another way of writing the same thing. Equals 0. So all I've used basically is the algebraic limit theorem to rewrite this. This here is true if and only if what's written below here is true. And so you could take the definition of derivative to be this. F has a derivative at x, and that derivative is capital A, which is a real number, if and only if this limit statement holds. All right, so is this ready to be upgraded into higher dimensions? So let's say instead of the domain being a subset of R, let's say the domain is E, some subset of Rn. Let's assume it's open. And for the codomain, let's make that Rn. So what needs to change here? Well, one thing that we can immediately notice is that the inputs to f and this h here are now vectors. They're vectors in Rn. So let me put vector symbols above them. So here by vector, all I mean really is they're lists of numbers. They're n-tuples. So these are now n-tuples. And there's something that doesn't make sense. Actually, I'm going to stick to what's written below. Forget this way of writing it. There's something here that doesn't make sense now, which is that it looks like I'm trying to divide by a vector. That doesn't really have a meaning. I haven't given that any kind of meaning. But it's harmless to put norm bars around everything. So that we could have done in the one-dimensional case and not changed anything about the definition, right? If the limit of a function at a point is 0 if and only if the limit of the absolute value, or the norm of that function, is 0. Okay, so now at least we've written something that makes sense. But what about this part? What kind of thing is A? That needs to change. So A needs to be such that what's written here makes the entire thing make sense. Okay, so what kind of thing is H? It's well, it's not anything. It's the dummy variable for this limit. So there's not like one particular H to talk about here, but for this function of H inside the limit, whose limit I'm taking, the H runs over n-tuple values. So this is kind of an n-tuple. And what does this thing as a whole have to be in order for everything to make sense? Well, it has to have the same type as what these output, right? And that's that it has to be an m-tuple. So now I know what kind of thing A must be. It must turn n-tuples into m-tuples. In other words, instead of being just a real number, you could say A has to be a matrix, but let's be really, really direct about what A is. Let's just directly say it's some map that turns n-tuples into m-tuples. And I'm going to assume it's a linear map. Why linear? Why not just any old map? Well, that's actually the point of derivatives. The point is that they're supposed to be a linear or first-order approximation to a function at a point. So if you look at the earlier definition of derivative, let me just show you that in that situation we were making linear approximation. So here I've put us back to the previous situation where f is a function of one variable with a one-dimensional output. And now I can put norm bars here, or absolute value bars, but I don't need to. And I just want you to see that if I view this object, which has to turn a number h is a real number, into a certain number the way in which a number h is turning into another number is by multiplying by a. That's a linear map of this type from R1 to R1, or just from R to R. So you could think of A in the previous setup as being a linear map from R to R. It's not literally that, but it's really similar, because the collection of linear maps from R to R is can be identified with R itself. As vector spaces, they're isomorphic. And there's one, they're not just isomorphic, but there's one very special particular isomorphism that immediately stands out, namely the one where if you have a number like, let's say L, then it well, that's a confusing letter. Let's say a number like y in the reals, then that corresponds to the mapping h goes to y times h. So to relate the old setup to the new setup, you can view the derivatives that were being treated as real numbers earlier as in fact linear maps from R to R whose effect is to multiply by that real number. So let me go back to the old setup. Now the definition of derivative is going to be something that generalizes our old definition of derivative. Okay, let's officially write down the definition of derivative. And this is going to be definition 9.11. All references are from Baby Rudin. So here's the setup. Assume you have a function from an open subset of Rn to Rm, and the domain is an open set, and assume you have a point in the domain. So this is the setup to talk about a derivative. Then what's the derivative of f at x? So if there is some A, some linear map A from Rn to Rm, such that this limit where, I could put norm bars here or not, that doesn't really matter, but I do have to put norm bars on the h down here, is 0. If there is some A that does this, then we define the derivative of f at x, also known as f prime x, to be that A. So this is the definition of the derivative of f at x. So then the derivative of f at x is a certain linear map from Rn to Rn. And that means we're sort of allowing this new notation to override some older notation. So previously, if you had a function of like this, a function of one variable with one output, we had previously defined that in this situation, f prime x would be a real number. The slope on the graph, right? The slope is a real number. Now we're changing that. Instead, it's going to be a linear map from R to R. And they can be thought of as the same thing due to this identification. But, they're not literally the same thing. Other conventions here. So I'm sticking with the Rudin terminology and using this notation, and I personally like this notation also, but one thing that you also see people using is df subscript x. They will call this the differential of f. Sometimes it's also called the Jacobian derivative of f, and people will write something like j of f of x or something like that. But this is going to be our notation. So that does mean we're overriding earlier notation. Derivatives are no longer numbers, they are these more complicated sort of data structures.